This video is going to look at viewing the probability of a singular outcome with positive density as greater than 0, and is divided into 3 parts. Part 1. Probability mass and probability density functions, and why areas don't necessarily apply to the singular outcome case of a continuous random variable. Part 2. Using the result in Part 1 to explain the PDF of an order statistic. And Part 3, why this matters, and concluding remarks. So let's get started with Part 1. So here I have a 6-sided fair die. I'm going to roll it and see what we get. It came out to be a 6. Does this mean that we should expect to get 6 more often just because of that throw right there? No. This is a fair die. And if we want to understand what's the probabilities of getting any of these different outcomes, we need something called a probability mass function. In this case, because it doesn't make sense to favor one side over any other, we would expect the likelihood or the probability of getting each of these on the die face value. We should expect them all to be the same. Now, a probability is a number between 0 and 1. And if something has, say, a 0.56 probability, generally that means that there's a 56% chance of that happening. So given that we know that, all of these probabilities have to sum to 1 because the only possibilities are getting these 1 through 6 values for a fair-sided die. So therefore, the probability mass function, I've written here PMF, that's what it stands for. This here would be 1/6. But now say we want to multiply this 1/6 by any positive constant, say a 12, for example. What we would get is this here. Now, this would no longer be a probability mass function, but you can still think of it as a mass function or a frequency function. And the important point is that this information displayed here is actually the same as the probability mass function over here. And the reason for that is this tells us the same ratio that we can expect between 1, 2, 3, 4, 5, and 6. So whether we have 1/6 for all of those or 2 for all of those, it's still a 1-to-1 ratio for all of these 6. So the important thing to note here is that the ratio of getting these outcomes here is going to be 1 to 1 to 1 to 1 to 1 to 1. That's the important point to understand here. This displays all of the information that we're looking for, even though it's not a probability mass function anymore. It can just be thought of as a frequency function. So now I want to look at this over here. What I've drawn is a function f of x equals x squared, and we're only considering that x can take on values between 1 and 4. The density is 0 otherwise. I'm calling this a density function here. And what is a density function? Well, it's just like this mass function here, except we have an infinite number of outcomes because we could get anything in between 1 and 4, including decimals, so 2.73 or anything in between 1 and 4. That is a possibility that we could get if we want to look at a density function like this. It tells us the ratio between of all the different possibilities indicated by the height here. So it's the f of x that is like the frequency we had over here, and the x gives us all the possible outcomes that we could get. Now, we want to use this to determine probabilities. That's what probability density functions in fact do is they help us determine probabilities. So how would we go about doing that? Well, over here, we have a 2. If we want to know the probability of getting a 2 or a 3, we could sum up the 2 for this one and the 2 for this one and divide it by the total number of you can think of it as samples here, which is like 12 random draws or 12 random samples. And if we want to know the probability, we just of getting a 2 or a 3, we just take the number here, the frequency of getting a 2, and the frequency of getting a 3, that's 2 times 2, over the total, which is 2 times 6. And that the 2's will cancel and we'll simplify by getting 1/3. It's the same idea here. If we wanted to get, say, a value that that you can see denoted by these red lines here in between the 2 and the 3, we'd have to sum up all of these f of x values, which you can think of as like the frequencies, and then divide it by the total in the sample, if you will, which is going to be all of these black numbers from 1 to 2, all of the red ones from 2 to 3, and all of the black ones again from 3 to 4. So if we want the probability of getting some value the probability of getting some value between 2 and 3, what we have to do is we have to add up all these f of x's here in the red. I'm just going to denote it with the red lines here. This is not a number, or it's not even, I'm representing it with 4 lines, but it's not 4 lines. It's actually all of these lines here, the values of f of x, in between 2 and 3. So there's an infinite number of them. And we'd have to divide it by everything. I'm using these lines to denote all of the possibilities between 1 and 2. These ones to denote the same as these ones, between 2 and 3. And I'm run out a little bit of, I've run out of room here, but, and I'm using these lines to denote all the f of x values between 3 and 4. Okay, so that in fact would be the probability. But the thing is, we have an infinite number of possibilities here. So that still seems to be like a bit of a problem. But remember back here, I said that we could multiply this 1/6 probability by any positive constant, any positive real number, and the information would not be changed. So let's multiply the top and bottom by an infinitesimally small quantity. I'll call it dx. The information and the probability here of the distribution, it's not changed by doing that. We've just multiplied it by an infinitesimally small amount on both the numerator and the denominator. So now what do? Well, what we have here is these numbers in between 2 and 3 for the red. We're summing up all these f of x values, but there's infinitely many of them. So if we take each of those values and multiply it by that infinitesimally small amount and sum them up over all of these red lines here in between 2 and 3, well, doesn't that sound a lot like the integral from 2 to 3 of f of x dx? The integral is, you can think of it as the area under the curve. So to find that, we're just taking all these f of x values and creating little rectangles here, multiplying that small change here in the x, and then by the f of x value. And if we sum all of that up in the limit, that will give us this integral right here. So we can do the same thing on the bottom. And on the bottom, we have this these lines representing from 1 to 2, the red lines again from 2 to 3, and these lines from 3 to 4. So altogether, that's the integral from 4 to 1. And it would just give us that. And now we've calculated the probability that x is in between 2 and 3 because we've taken all the frequency values, summed them all up, and divided by the total number in the sample, if you will. Now, since we can choose any constant to multiply these frequencies, these probabilities, or really the ratio, whether it's on a continuum or the ratios on a discrete random variable here, what we can do is multiply that by anything. Now, I've chosen this function here to be f of x is equal to x squared. But what you'll notice is this denominator here, if we integrate this, f of x being x squared, from 4 to 1, that will not turn out to be 1. So to change this from a density into a probability density, all we have to do is take our f of x and multiply it by some constant k, such that the integral of k f of x dx is equal to 1. Now, you can work that out. I'm not going to do that here. But that k will not change the information from the distribution. But what it will do is make this denominator here, once we have the k, it will make the denominator equal to 1. So why would we want to do that? Well, we want to extract probabilities from this distribution. So by turning it into a probability density and multiplying this by k, now we only have to evaluate one integral. Because if we had this function here and we've solved for whatever the k is, and we wanted to know the probability between 2 and 3, we could just integrate between 2 and 3 and just putting the k here. Again, I've run out of room, but just multiplying it by that k, and that's all we would have to do to evaluate this probability, because this bottom here, the denominator would just be 1. So that's what a probability density function is. Now, in this video, or in the title of this video, I should say, I've said viewing the possibility of a singular outcome on a density function with positive density. I say viewing it as greater than 0. I want to view it as greater than 0. So what do I mean by that? Well, say we have, get rid of all this. Say we have a value, of a singular outcome here that's maybe 2.5, and we want to know what's the probability of getting that specific value. Well, if we look back to here, when we integrate over the bounds from 2 to 3, that gives us what we are looking for. So if it's just 2.5 as a singular point, you might say, well, it's just the integral from 2.5 to 2.5 of f of x dx. And I'll just call this f1x because it's not the same as this. I'm treating this f1x as a true density. So what is that going to be? Well, to evaluate this, to evaluate integrals, we need to find the function that when we take its derivative, it gives us this f1 at x. So that would just be some big function f at 2.5 and this is a function evaluated at 2.5 minus that same function evaluated at 2.5. So that would seem like 0 makes sense here. But the thing is, Areas that are one-dimensional, you have some length here, call it B, and you have another length here, call it A. To get this area, all we have to do is multiply B by A. But what happens when A is 0? We still have a line, but the thing is, there is no width or length to this. It's just, if you look at this as the width and this is the length, or this is the length and this is the width, whichever way we want. Remember, area is a two-dimensional value that calculates the surface covered by whatever we're trying to take the area of. So if this is 0, it's just length by width. B times 0 is again going to give us 0. But is this really what this distribution is telling us? Well, if we can get anything between 1 and 4, we would say, the probability of a 2.5, it might be infinitesimally small, but maybe it shouldn't be viewed as being exactly 0. Let's do the same trick we did before. So the probability that the random variable x takes on 2.5 is just the function I'm calling it f1, and I'm letting that be k times x squared. So that is a true density, a true probability density. F1 evaluated at 2.5 over these black lines. I'm indicating all the f values starting at 1 up to but not including 2.5. The f1 value at 2.5 plus the f values that are greater than 2.5 summed up. That's indicated here. So pulling the same trick that we did before, multiplying the top and bottom by dx, we'll just get f1 at 2.5 times dx over 1. So generalizing, what we'll get is the probability the continuous random variable is equal to exactly x is equal to f of x dx in the context the dx is an infinitesimally small amount. Part 2. Using the probability of the continuous random variable being x as f of x dx to explain the PDF of the kth order statistic given by f of x sub k equal to n factorial over k minus 1 factorial n minus k factorial times little f of x, which is the PDF of a sample, times big F of x to the k minus 1, where big F of x is the cumulative distribution function, times 1 minus big F of x to the n minus k. Okay, so let's get started with part 2 then, order statistics. Basically, when dealing with order statistics, what we do is we have a sample of size n drawn under IID conditions. So IID means independent and identically distributed. And xk is the kth lowest draw, or the kth order statistics. So x1 would be the minimum draw, xn is the maximum draw. The analogy people like to use with this is that of a race. So maybe like a 100-meter dash, where we want to measure the performance of 10 athletes or however many were competing, and whoever's time is the lowest, that time in seconds would be x sub 1. And whoever's time was the slowest, that would be x sub n. And if we want to know, what was the fourth place time, that would be x sub 4. So basically, that's the analogy people like to use, but this formula we're going to develop for the PDF of the kth order statistics, it only works under IID conditions. So to explain the probability density function of an order statistic, I'm going to use what I talked about in part 1, viewing the probability of a specific value x as f of x times dx. P here is probability, f of x is the density, and dx is a small amount. So if we want the probability that the kth order statistic is some value x, well, first we need the kth order statistic to be this x, so one of the values has to be x. So the probability of it being x is just f of x dx. Now there's n in the sample, and we want the kth order statistic. So what we want to do is realize that this is one sample is here, but k minus 1 have to be less than this. This big F here is the cumulative distribution of F, which tells us the probability that the random variable is x or less than x. So it's in that range from the lower bound up to x. So that will be k minus 1 less than x. What's left? Well, there's n minus k left that have to be greater than x. And to get greater than x, we just take the complement here, 1 minus f of x. And that's raised to the n minus k. But this is not really the whole thing, because now we have to look at how many different ways can this happen. Like, for example, the kth order statistic, it can come from any one of the n samples. So actually, what we have to do here, need a little more room. First of all, for the kth order statistic to be exactly x, well, that can happen in any of the n ways, because there's n different samples here, and any one of them could end up being the kth order statistic. So n, and for each of those n's, we can have, of the remaining n minus 1, we can choose k minus 1 to be less than this. So that's just a little combinatorics here, n times n minus 1 ck minus 1. And that will give us all the different possibilities of the different ordering of the samples. So we just want to do a little rearranging here. This is n multiplied by n minus 1. N minus 1 factorial over k minus 1 factorial, and then the difference, n minus 1 minus k minus 1. And then all of this stuff remains. I'll just denote it like that. N times n minus 1 factorial, that's just n factorial. k minus 1 factorial remains the same. Minus 1 and plus 1 will cancel, and we just get n minus k factorial. And now I'll just write it. Okay, so remember we have probability is equal to the density times the infinitesimally small amount. So here's the probability. We have all of this multiplied by the infinitesimally small amount. So what's the density we're after? It's this right here. Part 3. In this third and final part of the video, I want to look at why p at x equals f of x dx for a PDF matters. For this, I'm going to look at a fictional scenario, but one that could possibly play out in the real world. This scenario deals with A1C blood test values. From this slide, we can see that Diabetes Canada says that if A1C values are 6.5% or higher, generally this leads to a diagnosis of diabetes. Okay, so in this scenario, a random patient goes for a blood test, and half the vials are sent to lab A and the other half are sent to lab B. And lab A says that the A1C value is 6.4%, while lab B says that the A1C value for the same patient is 6.6%. Now that could be a bit of a problem because, as we saw on the slide, the critical value for assessing whether a patient has diabetes is 6.5%. So here lab B is saying that the patient does have diabetes, while lab A is saying that the patient does not. Now what we're going to do here is assume that one of the results is correct, which is not really that bad of an assumption, because if both labs A and B are reputable labs, we would expect that one of them got it right, or at least very close to the actual true value. Here I've drawn the PDF of A1C values in the general population. Now this is just a fictional PDF. I don't know what the true PDF looks like for A1C values in the general population. But we know that 5.5 and less is considered normal, so we might expect to see, the maximum of this PDF be at 4 or a little bit less than 4. So in this case, what we want to do is we want to understand what's the likelihood that lab A is correct or lab B is correct. So again, this is just a fictional drawing here of the PDF, but the density at 6.4 looks about twice the density at 6.6. So I'm going to make that assumption that the density F evaluated at 6.4 is equal to twice the density evaluated at 6.6. So that's just another assumption, but that's because I don't know what the true underlying distribution looks like here, so I just drew something that I thought might look like the real distribution. So if we want to work out, well, what's the probability that A is correct? So the probability that A is correct, given that A or B, labs A or B, is correct, is equal to what? It's going to be equal, A is correct if the value is 6.4. So what we want is the probability that the random variable is equal to 6.4 divided by the probability that, the probability that the random variable is equal to 6.4 plus the probability that the random variable is equal to 6.6. Now remember, this is a continuous random variable, so the probability of a particular point, if we just assume that to be 0, we're going to get 0 over 0 here, and that's not very useful. So let's look at what I talked about in parts 1 and 2 of this video. The probability of getting a specific value x on a continuous probability density function is equal to the function evaluated at x times that infinitesimally small amount. Now we can say the probability that a is correct is the probability that the random variable is 6.4. That's just the probability of 6.4 f at 6.4. Times dx all over f at 6.4 times dx plus f at 6.6 times dx. Now, since I'm assuming here that dx is that infinitesimally small unit, we can just get rid of all of these. And f at 6.4 is 2f at 6.6 by assumption. So what we end up here with is we're able to cancel out all of these, and we just get 2/3. So if the probability that lab A is correct is equal to 2/3, we might say, well, since A is correct 2/3 of the time, maybe this patient doesn't have diabetes, and it might be wise to not put them on medication for their A1C values. So in conclusion to this video, viewing the probability of a continuous the probability of getting a specific value for a continuous distribution as f of x dx, it has its problems because, like, a probability is a number between 0 and 1. Dx, like, how do we determine what that is in terms of digits? We really can't, because it's just, you can just think of it as that independent infinitesimally small amount. And there are other problems. I mean, usually when we look at dx, it means that we are taking some kind of limit. We don't really view it as just some number times some infinitesimally small amount. But I do think that there is value in viewing the probability of a continuous random variable getting a specific outcome of x as f of x dx. Because it will allow us to maintain the information of the distribution, and it will allow us to make predictions about outcomes for patients like we saw here, or really not only in the medical field, but really any field that is interested in predicting outcomes of random events on a continuum. So we finally reached the end of this video, and I just want to say thank you very much for watching.